Hi everyone, and welcome to the first topical video of our Unit 9 remediation series, where we're going to be looking at physical change math related to gases. So the first thing we'll discuss here is how we conceptualize gases, how they move and behave, and then use the combined gas law to make really powerful mathematical predictions about how a change in external conditions is going to affect particle spacing. So using the PVT equation to help solve problems like the one you see at the bottom of the screen, where we're given a set of initial conditions and need to predict how the volume, temperature, or pressure of that gas is going to change when we change either the volume, temperature, or pressure of that sample. So first, let's think about how gases look and behave in an ideal fashion. When we say the word gas, what's probably coming into your head is a particle diagram where particles are spread very far apart, they're spaced randomly, and they move at high speeds without really interacting with one another. Remember, gases are the phase of matter with the highest entropy, and what's unique about that is that changes in external conditions will really affect how much space they take up. Given this box of particles, you can imagine that if I change the temperature, let's say I increased it, these particles would start bouncing around much, much faster. And their desire to move around faster is going to put more pressure on the outside of that box. They're going to keep slamming into the sides. And if we can't hold a constant pressure or can't hold a constant volume, that box is going to expand. Likewise, if I took that box and just made it smaller, those gas particles would bounce into one another and the walls of the container more frequently, resulting in an increase of pressure. So with gas particles, we know that these changes in external conditions affect how the particles behave, and more specifically, how far apart the particles are. If you remember, we've put P, T, V across the hulls of paper before to try and make predictions about how conditions are going to change if at least one of those three variables is held constant. So let's say in this box, I'm maintaining constant temperature. I'll cover that up and say, if I decrease the volume of that box by moving V down, I see that P moves in the upward direction, meaning that pressure would increase. Inversely, if I move volume up, saying I'm going to make the box bigger, pressure will decrease. If I'm able to keep pressure constant, maybe I want to increase the temperature. Moving temperature up also makes V move up, showing that an increase in temperature leads to an increase in volume. This quick predictive tool does allow us to make some qualitative predictions about the behavior of gases, but doesn't allow us to extend into the realm of mathematics where we can actually say how much the pressure, temperature, or volume increased or decreased. In order to do that, we're going to have to use the combined gas law, which you can find on your reference tables on table T. As you can see, it's the only equation that involves pressure, temperature, and volume combined together. Those different variables do show up in different equations, like the density equation or maybe the heat equations. But if we're dealing with scenarios that involve changes in pressure and volume, or changes in pressure and temperature, or even changes in all three, we're going to have to use this combined gas law to make our mathematical calculations. So let's take a look at an example problem and relate it to the idea of ideal gases. In this particular problem, we're asked to calculate the new volume of a sample of N2 nitrogen gas that once filled a flexible 2-liter container at STP, but had its pressure changed to 5 atmospheres and its temperature decreased to 100 Kelvin. The way I like to approach these problems is to look at where did I start and where did I end? What pieces of information are given to me, and what is it that I need to find out? So right off the bat, I see we're calculating a new volume. So that already dictates what equation I might be using. We're down to either density or this combined gas law. But given that we're dealing with a sample of gas, chances are we're probably going to be looking at the combined gas law itself. At one point, this gas filled a flexible 2-liter container. I'll underline that 2 liters as an initial condition of volume, V1, the volume I started at. It also said that our gas sample initially was at STP, standard temperature and pressure. This, though it doesn't look like it, gives us conditions of temperature and pressure that we can look up on our reference table. So I'll mark this as T1 and P1. Now we note that it had its pressure changed from whatever was standard to 5 atmospheres. So I know that this is going to be my new pressure, and its temperature was decreased to 100 Kelvin. So this will be my new temperature. Writing out the combined gas law equation shows me that these variables are linked in a very specific way. I've got all of my information in my problem and in my reference table, but I just need to know where to plug the numbers into. So I'll create sort of a shopping list of where I started and where I ended and figure out what it is I need to calculate. So the problem told me that I started at standard temperature and pressure. And if you ever forget those values, don't fear, because they're right on the very front of your reference table. It says here that standard pressure is either 101.3 kPa or 1 atmosphere, and standard temperature is 273 Kelvin or 0 degrees Celsius. Given the constraints of my problem, I know that pressure is changed to something in atmospheres, so to stay consistent, I'll pick the 1 atmosphere. And since in all combined gas law calculations, temperatures have to be in Kelvin, I'm going to choose the 273 Kelvin. That just keeps our values positive since the Kelvin temperature scale does not have negative values. So since we started at STP, we'll put our initial temperature at 273 Kelvin and our initial pressure at 1 atmosphere. Our starting volume reported in the problem was 2 liters. And then I just need to figure out, okay, this is the snapshot of where I began. How did it look when I made changes to the environment? So what was the new pressure? What was the new volume? And what was the new temperature? Looking to the problem itself, I noticed that I did change the pressure. I increased it to 5 atmospheres. And I did decrease the temperature to 100 Kelvin. I want to calculate the new volume, so it makes sense that V2 is going to be my X. This is where you're going to move on to plug the numbers into that equation to try and solve for that value of X. So for P1, I'm going to plug in 1, V1, I'll plug in 2, and T1, I'm going to plug in 273. For P2, I've been given that value as 5. V2 is my unknown, so I'll leave it as X, and T2 is 100 Kelvin. At this point, people usually feel comfortable doing cross multiplication to solve this problem. So 1 times 2 times 100 equals 273 times 5 times X. Plugging those values into your calculator will give you 1 times 2 times 100, 200, equals 273 times 5, 1365X. Remember here, folks, it's very careful that you stop and think. Remember, you're solving for X, so you need to get rid of anything attached to X. And in this case, that's the 1365. So dividing through by 1365, 200 divided by that value gives you 0.1465, which you can round if you like, usually to the nearest hundredth or so for this problem seems appropriate. Remembering units, this was volume we were solving for. Our initial units were liters, and that's where we're going to end. If we think about this problem, what we see is that this gas has made a change because its pressure was increased and its temperature was increased. In the result, the volume decreased rapidly. Pause and think about it for a minute. Does that make sense? If I increase the pressure and decrease the temperature, will that make a gas's volume decrease? As one last thing to think about, consider what's going to make a gas behave most like a gas does in your mind, with its particles spread far apart. Does it need high temperatures or low temperatures? High pressure or low pressure?